All right, let's take a look and see what we've got here. Let's look at let's look at those points there, which don't look lovely, but we're fine. So here are some points. We've got -2, -9, -12. We have Q is given by -6, -6, -7. -7? No, +7. And R is 3, -4, -4. And we're asked to find the side lengths and all three angles. All right, we'll get to this in a minute. So let's talk about angles for a second. Let's talk about the dot product. So we'll come back. We're coming back. Go away. The dot product. Let's see, sure. So if you're given two vectors, I usually call them U and V, and some angle in between them, there's a couple of different ways of thinking about and or calculating the dot product. Oh, and then just 1 second, let me do one thing here. Why are you over there? Yeah, come back over here. Okay, great. I want to try my video. That's what I was ready to do. There we go. There we go. Cool. So the dot product, U dot V, it is important to write the dot there so you can see it, is equal to the length of U times the length of V times cosine of the angle between them. Okay, so I don't love these examples here. Sure. So for example, the vectors, sure, we'll go that way. U equal to 5, 0, and V equal to 3, 3. Most examples, you cannot calculate this way. This one is an example where we can. So I'm going to draw them. Okay, great. U is 5, 0. So there's my U. And V is 3, 3. So there's my V. And in this example, it's easy for me to see what the angle between these two vectors are. It's clearly a 45-degree angle or pi/4 radians. So to find the dot product, U dot V, it's equal to the length of U times the length of V times cosine of the angle between them, which in this case is going to be, okay, the magnitude of U is going to be, just going to be 5. But you could write the square root of 5 squared plus 0 squared. The magnitude of V is going to be the square root of 3 squared plus 3 squared. And multiply by cosine of the angle between those two vectors. So in this case, we're going to get the square root of 25, which is 5. The square root of 18, which you could write as 3 root 2 if you preferred to. And cosine of pi/4, which is the square root of 2 divided by 2. Normally I wouldn't, no, that's not true. I would totally simplify this. So that's 5 times 3, which is 15. And then root 2 times root 2 is 2, divided by 2 is 1. So actually, the dot product here is just 15. Or you could do it the usual way, which is when you take the dot product of two vectors, the way that we actually calculate, oh, so this is the actual definition of the dot product, is where it's the length times the cosine of the angle between them. But the way we actually typically calculate the dot product between two vectors is by saying that it's equal to the sum of the products of the corresponding components. So in this case, 5 times 3 plus 0 times 3, which is 15. Which is really nice when you don't actually know the angle between the two vectors. Oh, I should say all that too. So don't worry, we'll make our way back to these questions, I promise. They're not on my mind. A few other things to point out here. I know I've mentioned the other notations a little bit, but let's talk a little bit about a standard notation, which is the IJK notation. So in the three-dimensional coordinate system, there are 3 unit vectors. That's the length of 1, that's the length of 1, that's the length of 1. And we call these vectors, well, the one that's in the x direction, we call I. The ones in the y direction, we call j. I mean, they go alphabetically, right? X, Y, Z, I, J, K. And the one that's in the z direction is k. This is pretty standard notation for unit vectors in the 3 standard directions. If you were talking higher dimensions, you would start using notation like E1, E2, E3, E4, etc. So just as a point, although I don't think you really need to worry about this, if you were, say, in R5 with 5 dimensions, you could say that your first standard basis vector is 1, 0, 0, 0, 0. Your second one is 0, 1, 0, 0, 0. And I think you get the idea all the way to your fifth one would be 0, 0, 0, 0, 1. That's kind of how you find a, I know I'm saying words that you might not have heard, a standard basis for this vector space, but those are the words. I don't really have an explanation for them at this moment, but those are kind of the important vectors that we like to write all the other vectors in terms of. So for example, when I'm thinking of the vector 2, 5, -3, I could think of it as 2 times I plus 5 times j minus 3 times k. And we typically stop writing the arrows over I, J, and K because it just gets to be kind of a pain in the butt. But that's pretty standard notation as well. So we could ask to say, like, I want to find U dot V given U equal to 4, 2, 1, and V equal to the vector above 2, 5, -3. And the way we do this is very straightforward. U dot V, you're just taking the x components and multiplying them together, the y components and multiplying them together, and the z components and multiplying them together. And then adding it all up. So this is going to be 8 plus 10 plus -3, which happens to also be 15. Purely coincidental. What else to say here that's super important before we get too deep into this? Yeah. Yes, question.
We can do like the dot product by just following what we already know.
When you say what we already know, I assume you mean doing it this way.
Yeah.
Okay.
What situation?
Excellent question. What situations would we use the other dot product in? Well, probably the most typical example is something like, what is the angle between the vectors? I'm going to make it easy this first time. 3, 3, and -2, 2. Here's the idea. We're going to say, well, we can calculate the dot product in 2 different ways. We could either say the dot product is going to be the magnitude of u times the magnitude of v times cosine of the angle between them. We could also say it's just the components of u times the components of v added up together. I'm using pretty standard notation here, right, where we're imagining u is the vector u1, u2, v is the vector v1, v2. So then we can use this equality to solve for cosine. So we can say that cosine of theta is equal to u dot v divided by the magnitude of u times the magnitude of v. I don't prefer to write it out this other way, but you could also think of it as just, the way we calculate the dot product, u1, v1 plus u2, v2 over the magnitude of u times the magnitude of v. So this is an occasion, that's why we would want kind of both definitions, so that we can do something like find the angle between two vectors. In this case, let's check it out. If we find, so let's see, so the magnitude of u, I'm gonna say this one's u, and this one's v. So the magnitude of u is the square root of 3 squared plus 3 squared, which is the square root of 18, or 3 root 2. And the magnitude of v is the square root of negative 2 squared plus 2 squared, which is the square root of 8, or 2 root 2. So then cosine of theta is going to equal u dotted with v, so 3 times negative 2 plus 3 times 2, all over 3 root 2 times 2 root 2. I probably didn't need to do all that work for the bottom part, because in this particular case, the numerator ends up equaling what? Zero. And 0 divided by not 0 is still 0. So if cosine of theta is equal to 0, our angle better be... What angle do you take cosine of and get 0? In degrees or radians? And cosine of 0 is 1. Pi over 2, or 90 degrees. This actually comes to a really important fact about vectors. We say that u and v are perpendicular if and only if, which is an if with two f's. That's what IFF means. It means if and only if the dot product of u and v is equal to 0. So if someone ever asks you if two vectors are perpendicular, what they're really asking you to do is take their dot product and answer the question, is it 0 or not? If the dot product is 0, yay, they're perpendicular. If the dot product isn't 0, they are not perpendicular. Also, going along with that, since cosine of theta is equal to the dot product divided by two things that are both positive, if the dot product is positive, then cosine is positive and the angle is in quadrant 1. If the dot product is negative, which means cosine is negative, the angle is in quadrant 2. So the sign of the dot product fully determines if your angle is acute or obtuse. I guess I could write that down. So just to point out, why is it all white over here? That's terrible. So if u dot v is positive, then cosine of your angle between them is positive, which means your angle is acute. Your angle is between 0 degrees and 90 degrees. And if u dotted with v is negative, I guess it could end up actually being equal to 0 degrees. That's what I meant to, oh my gosh, that's terrible. Right, if the vectors point in the same exact direction, then their angle between them is 0. And then if the vectors point in the opposite directions, or if the angle between them is obtuse, then cosine will be negative, because cosine of an angle in quadrant 2 is negative. And here theta will be obtuse, which means it's going to be bigger than 90 degrees, all the way up to 180 degrees. Wow, obtuse is? No, obtuse. Okay. So, there's water everywhere, sorry. So now we can answer some questions about angles between vectors and lengths of sides. So back to this question that started us off and going down this road here. Here are the points. We want to find the side lengths and the angles. Blech. Okay, so you don't really need to draw this picture, but it might help you keep things kind of in order. So if I want to find, say, the angle, let's say the angle at P. So I want to find this angle. I'm going to need to find the vectors that emanate from P. So I'm going to need to find the vector PQ, which is the Q minus the P. So -6 minus -2, -6 minus -9, and 7 minus negative 12. Yeah. Is that a 2? That's a 2, not a 12. 7 minus negative 2 is 9, not 19. And then we need to find PR as well. So PR is going to be the R coordinates minus the Q coordinates. That's going to be 3 minus negative 6. Sorry, the R coordinates minus the P coordinates. Apologies. 3 minus negative 2, which is 5. Negative 4 minus negative 9, which is negative 4 plus 9, which is also 5. And negative 4 minus negative 2, which is negative 2. And I've written those as points, which is terrible, right? This is not the good. Actually, they should be little slanty brackets because that's how I like to write my vectors. And these are definitely vectors, not points. Sorry, my notation is looking grosser and grosser by the minute. All right, let's do a double check just to make sure we didn't make any mistakes. PQ is negative 6 plus 2, which is negative 4, negative 6 plus 9, which is 3, 7 plus 2, which is 9, and PR is 3. This is a positive 3 right now. Plus 2, negative 4 plus 9, negative 4 plus 2. Okay, looks all right. Questions so far? Okay. And yes, we could find QR as well. We will do that, maybe. So then the magnitude of PR is just going to be the square root of, sorry, the PR first. 5 squared plus 5 squared plus negative 2 squared, which is the square root of 25 plus 25 plus 4, which is 54. Correct. Yes, I know. There's a lot of little marks here that are masquerading around as looking like they might be minus signs, but they're really not. Yeah, it is definitely 3 minus negative 2 there. That's the way some people write the magnitude. You could write it also just as one line. So you can write it as this way. You could also write it as this way. Both notations are totally fine and used all the places. So yeah, this is more of a linear algebra notation, but your teacher might use that also. Magnitude of PQ is equal to the square root of negative 4 squared plus 3 squared plus 9 squared, which is the square root of 81 plus 9, which is 90, plus 16, which is 106. Gross. And we don't need to worry about simplifying any of those. So then the angle between them. So honestly, I prefer the formula that starts with cosine of the angle equal to the stuff. So the formula I can remember isn't theta equal to the inverse cosine of whatever. It's cosine of theta is equal to PQ dot PR over the magnitude of PQ times the magnitude of PR. That's how I like to start off, just because it feels less gross than writing inverse cosine. So then we actually calculate this. PQ divided with PR is, so it would have been smart here, in case one of these ends up being 0, to do the dot product first, right? If this dot product ends up being 0, I just wasted a couple minutes finding those magnitudes. I don't think it's going to be 0, but just to point out, like you should think about that when you do it. So PQ dot with PR is going to be negative 4 times 5 plus 3 times 5 plus 9 times negative 2, all divided by the square root of 54 times the square root of 106. Yeesh. And then you're going to get negative 20 plus 15 is negative 5 minus 18 is negative 23, all divided by the square root of 54 times 106. Yeesh. It's not lovely. So then the way you find the angle is by using a calculator. Or just typing in, if this is a WebWork problem, in WebWork you can type in theta equal to the inverse cosine or the arc cosine of negative 23 over the square root of 54 times 106. And if that doesn't come out right, it might be because this is giving you an angle in radians and it might want it in degrees, although usually they want it in radians. So this should spit out an angle in radians for you in WebWork if it's a WebWork problem. And if you have to change to degrees, you multiply it by 180 over pi. Although usually they want radians, typically. And then you do the whole thing again for one of the other angles. I don't think we need to do it again for one of the other angles. And then you don't, well, you can, but you shouldn't do it again for the third angle. For the third angle, you should take your first two angles and do pi, if it's in radians, minus the two values you just found. Meaning minus copy paste this, copy paste that, put them into WebWork. Blah, blah. Real fun. So that's the idea as far as finding the angles between vectors is doing this calculation. And then doing the arc cosine of the dot product divided by the product of the magnitudes. It gets a little messy, but it's not too terrible as far as things go.
So wait, God was the one that he-
Is that's angle P? Yeah, let's see. Go ahead. The PR is a vector.
Oh,
So just to kind of check this out, can you guys see that? And not really. But over here, kind of it. Yeah, sure. You can kind of see it there, right? Where? Okay. Let's see what we get here. So if I was calculating this, I would probably do the inside parts first here. So negative 23 divided by the square root of 54 times 106. And then I'm going to do the arc cosine of that. Interesting. I have to put the answer. I always forget that. So about 107 degrees. If I want that in radians, I could have either switched to radians before I did it or multiply this by pi divided by 180 to get approximately 1.87 radians. But really, if you're entering this in WebWork, you shouldn't do either of these things. You should just enter the whole expression in WebWorks and not try to enter a decimal approximation. Because hopefully you've all learned by now that WebWork isn't really a fan of decimal approximations. It wants the actual expression for the answer. Okay. Let's move along. Sure, we can look at the one below that, I think. Seems reasonable. There's lots of angles to consider here. Maybe we should start with the one below that, but okay. Well, things are upside down. All right. Wow, why are all these papers out of okay. Good. I will point out for the previous problem, we knew that first angle was going to be obtuse because the dot product was negative. So we knew the angle was going to be more than 90 degrees. Let's look at the one that says to find the coordinates of the vector of length 8. So we want a vector. And I'm going to write it this way. We want the magnitude of V to equal 8. And we want it to be in a direction of 70 degrees counterclockwise from the positive x-axis, which is where we should always measure our angles from if we have the choice. So I'm going to draw it. I do think a lot of these problems are worth drawing. We're going 70 degrees, so about this way. So it's going to look like that. And really, these problems mostly are trigonometry problems. We're being asked to find the x coordinate and the y coordinate. Question.
it's like some two axes.
Oh. So I would assume that means from the y-axis then, right? Typically, if we're thinking x1 and x2, we're usually thinking this is x1 and this is x2. So I've drawn this wrong for the way that that's written. I just didn't see the little 2 down there. Sorry about that. So instead, so this would be from the positive x1 axis. I will just to point out how you do this one, right? If I was trying to find the x and y coordinate, I would say that x is going to equal 8 times cosine of 70 degrees. And y is going to equal 8 times sine of 70 degrees. Because if you look at this triangle, right, cosine of 70 is x over 8 and sine of 70 is y over 8. So you can then solve for x and y. Well, let's do the other one. So the other one really, whoops, that's probably bigger than it needed to be. We're moving 70 degrees counterclockwise from the positive x2 axis. So we're really going like this. So there's probably like three ways you could do this, but I would say the most the most consistent way of doing something like this is to always just measure your angle from the positive x1 or x-axis. So what I would point out is this 70-degree angle measured from the x2 is 90 plus 70, which is 160 degrees from the x1. So I would think of this having an x coordinate, which is going to be 8 times cosine of 160 degrees, which will be negative, as it should be because it's gone to the left. And the y coordinate should still be positive. The y is going to be 8 times sine of 160 degrees. Alternatively, if you prefer a different way of doing this, you could think of the reference angle. What is the reference angle here? What is a reference angle? It's the angle you measure to the nearest x-axis, the acute angle. So if this is a 70-degree angle here, this better be a how much here? Yeah. So you could say, alternatively, that the x value is going to be 8 times cosine of 20 degrees. The y value is going to be 8 times sine of 20 degrees. But then we need the x value to be negative and the y value still to be positive. You could do it that way too. So yeah, that'll work. And really, you could, so I'll just point out, you could also do that for the next one. So for the next one, which is, let's read this very carefully here, length 5, 20 degrees counterclockwise from the negative x2 axis. Seems like you're making it harder on yourself. I mean, I know you're not specifically, but it seems like the problem is being like, why would you do it this way? So we're going 20 degrees counterclockwise from the negative x2 axis. So we're starting here, and we're going 20 degrees that way. So again, you could do it in, I think, two different ways. Oh, it's a length of what, 5? So you could either say your x coordinate is going to be 5 times cosine of 180 plus 20, which is 200 degrees. And the y value is going to be 5 times sine of 200 degrees. Or you could use the reference angle of 20 and say that x is going to be 5 times cosine of 20 degrees. Y is going to be 5 times sine of 20 degrees. But since we're in quadrant 3 over here, both x and y need to be negative. So you have to slap on some negative signs there. Either way, those are the same answers, just written differently. And I guess, right, if we were writing these as vectors, right, we would say that our vector here had component form 5 cosine of 200 degrees, comma 5 sine of 200 degrees. Or if you wanted, you could write it as 5 cosine of 200 times the I unit vector plus 5 sine of 200 degrees times the J unit vector. Both of those would be totally acceptable. Unless your teacher says they're not, right? These are all acceptable in the wide world of maths, unless your teacher says they want you to do it this way or that way. So make sure you're doing it the way your teacher said you should do it. Hopefully they're not too picky, because really there's lots of ways of writing vectors. Okay, let's see, there's one. Oh yeah, let's look at the one to the left there. V lies in the first quadrant, makes an angle pi over 3 with pi over 3, okay, with the positive x-axis, and the magnitude of V is 4. Find V in component form. So similar question. This one's going to have a slightly more simplified answer. Well, again, for these ones, if it's in 2 dimensions especially, I think drawing it is usually a good thing to do. Lies in the first quadrant, makes an angle of pi over 3 with the positive x-axis. So we're looking like that. Our angle is pi over 3, or 60 degrees. And it's got a magnitude or a length of 4. So almost any vector, especially if the angle is measured from the positive x-axis in the counterclockwise direction, you can always write it in its component form by just doing, in fact, let's just say very generally, for a vector v, it's going to equal the magnitude of v times cosine of the angle given and the magnitude of v times sine of the angle given. As long as theta is measured counterclockwise from the positive x-axis. That's like the standard way of breaking a vector down that's given as a magnitude and a direction into its component forms. So here, I mean, you can also draw more, but here our vector, well, the x component is going to be 4 times cosine of pi over 3. And the y component is going to be 4 times sine of pi over 3. And in this case, since pi over 3 is an angle that you were expected to know how to take sine, cosine, etc. of, we should simplify this more. We should write this as 4 times cosine of pi over 3, which is 1/2, comma 4 times sine of pi over 3, which is root 3 over 2. And then simplify it further as 2, comma 2 root 3. That certainly feels like a reasonable expectation if the angle is a pi over 3 or a pi over 6 or a pi over 2 or a pi over 4 or any known angle. Sure. Okay, cool. Do that. We'll get there in a second. So I will also point out that you can find angles between vectors in higher dimensions. So technically, you could find angles between vectors in 4 dimensions or 5 dimensions or 6, and that's where you really have to rely on the definitions here. But we could even do it in a three-dimensional situation, like we could find the angle between the vectors u equal to 1, comma 2, comma -2, and v equal to 4, comma 0, comma -3. There is kind of a neat chemistry question that I've seen done before, where they're like, you've got this, I don't know, I'm not good at chemistry. This chemical where you've got some thing in the middle, and then like it's spread out like in a tetrahedron, like equilaterally kind of, and then you can find like the angle between the two bonds by using the angle between vectors. It's kind of neat. Maybe we'll do that one later, not today. Yeah. So if I want to find the angle between these, it's just tossing everything into the formula. Cosine theta equals u dot v over the magnitude of u. And sorry, I wrote it the other way, times the magnitude of v. And in this case, I am going to be smart. I'm going to find the dot product first, just in case it's 0. So in this case, it's going to be u dotted with v, which is 1 times 4 plus 2 times 0 plus -2 times -3. Oh, good. It's not negative. So, well, I mean, it's not really good because I have to do more work. So on the bottom, the magnitude of u is the square root of 1 squared plus 2 squared plus -2 squared. So 1 plus 4 plus 4. And the magnitude of v is the square root of 4 squared plus 0 squared plus -3 squared. So it looks like on top we have 4 plus 0 plus 6. On the bottom we have the square root of 9 times the square root of 5. Sorry, the square root of 25, which is 5. And that ends up equaling 2/3. So then our angle is the inverse cosine of 2/3. Or if you prefer, and I kind of do prefer, the arc cosine of 2/3. Cool. Which, if you care, is approximately 48.2 degrees. But if I was asking this question or being asked this question, this is definitely the answer that I would submit, not the decimal approximation. Okay. Yeah. Got that one? Sure, that's fine. Yeah. All right, cool. Let's look at these last few questions over there. Find the line through the point 4, 0, which is perpendicular to the vectors 0, 4. Okay. I think for a lot of these questions, drawing the picture is really going to help us see what's going on. So I want the line to the point 4 comma 0. So I'm going to go over 4. So there's the point 4 comma 0. And it's got to be perpendicular to the vector 0, 4, meaning 4 up. So that's my vector that I want to be perpendicular to. So what kind of line am I talking about if I want to be perpendicular to a vertical thing, essentially? It's got to be horizontal, but it also has to go through the point 4 comma 0. So it can't be the line y equals 1 or y equals 2 or y equals 7 or y equals -3. It's got to be the line y equals 0. That's the only line that's going to be both perpendicular to that vertical vector and going through the point 4 comma 0. Now, yeah, let's ask a better question. What if instead I want the line through the point? No, that's fine. Yeah. Yeah. So same point. But now I want it to be perpendicular to the vector. Sure. 1 comma 2. That should work out fine. So here's what we're looking like. My vector is over 1 up 2. And I want to find the line perpendicular to that vector that goes through the point 4 comma 0. Was my little ruler not in here? Oh well. So I'm looking for the equation of that line right there. So how do I find the slope? Because really what I need is the slope of that line. I've got the point, 4 comma 0, but I need the slope. Well, what I really need is the vector perpendicular to the vector that was given to me. And this is where we're going to use the fact that perpendicular vectors have a dot product that is 0. So we can look at this vector and be able to easily come up with a vector that's perpendicular to it. I can think of 2 examples that are easy. I'm sure you all could too. I'm just trying to find a vector, let's call it W, where if I take the dot product of W with V, I'm going to get 0. Well, one good example is -2 comma 1. Or you can do 2 comma -1. Or any multiple of that, right? You can do -6 comma 3, but usually we try to make it as small as possible. So there's the vector that's a vector that's perpendicular to V. And then we can find the slope by just saying, well, okay, well, the slope of that is, right? We're going left 2 and down 1. So, that has a positive slope, right? That doesn't seem right. I feel like I've done something terribly wrong here. Oh, I said left 2 and down 1, but that is left 2 and up 1. Ugh, terrible. Ugh. I should have looked at my picture over here, right? Left 2, up 1. So the slope between these 2 points from -2, 1 and 4, 0, the slope is, well, it's over 2 and down 1. So the rise over run is 1 over -2 or -1 over +2. Right? My slope here is -1/2. I could actually like do the math, I guess. Right? It's the difference in the y's over the difference in the x's. I don't know why I've written a -2 there because I'm just losing my mind today. Sorry about that. The slope is actually -1/2. And then you could use the slope and the point to find the equation of the line. So trying to find the slope of a line, or I should say, trying to find the slope of a vector or a perpendicular vector. The slope of the line that contains this vector is just the y coordinate divided by the x coordinate, or this is the y component divided by the x component. And the slope of this line is the y component divided by the x component. The slope of any line that contains a vector is the y component divided by the x component, or the rise over the run. Find the plane. Yeah, that's what I was really looking forward to. So, plane equations are super fun, I think. Shocking, I know. This one says find the plane. So when they say find the plane, they typically mean find the equation of the plane. But the equation of the plane through the point sure. -9, -3, -5 with, so you could say which is perpendicular to the vector or whatever, or another more common way of saying that is with a normal vector of 2, -2, -5. So what that means is we've got some plane here. We've got some vectors sticking up out of it perpendicular to the entire plane, which we typically call n for our normal vector. And this plane happens to contain the point -9, -3, -5. Okay. Finding the equation of the plane wholly relies on the fact that the dot product of two perpendicular vectors is equal to 0. So I'll back this up for a second. We got time. You'll get enough time. So I want to point out, you don't need to write this part down. But when you find the equation of a sphere, what you're doing is you're trying to describe every point on the sphere. So we know that every point on the sphere is equally distant from the center. So when I'm thinking about finding the equation of a sphere, don't trust me, this relates. I'm not just saying it for the sake of saying it. If this is my point x, y, z, or it's over there, or it's over there, or it's over there, all those points, I can find the distance between each of those points and my center, which will make up a number 1, 2, 3, and the radius, let's say it's 4, and say, oh yeah, the distance between those 2 points, which is the square root of the difference in the x's plus the difference in the y squared, I didn't say squared there, sorry, plus the difference in the z squared, is equal to the radius. And if we square both sides, we get x minus 1 squared plus y minus 2 squared plus z minus 3 squared equal to 4 squared. Exactly what you'd expect. But this equation describes every single point that could be on the sphere. Because every point on the sphere has to be a distance of 4 from the center. In the same way, we are about to describe every single point that's on this plane. So I'm going to pick one arbitrary one over here. And I'm going to call it XYZ. But really, XYZ could be there, or there, or there, or there, or there. And the thing that's true about every one of these points that I've picked that's on the plane is that if I draw the vector from that point that I know to the point that's still on the plane, this vector lives in the plane, which means that vector has to be perpendicular to that normal vector. So I want to point out that I'm going to call this point P and this point Q, and I'm going to say that the vector QP must be perpendicular to our normal vector. And that is true no matter what point I picked in the plane. Cool. Great, let's find the vector. The vector QP, well, again, it's the endpoint minus the initial point. So it's going to be x minus -9, y minus -3, z minus -5. And we know the vector n is already this vector 2, -2, 5. And now here's the result. These vectors have to be perpendicular, which means their dot product has to equal. Right. So great. QP, yeah, sure. No, let's write the n first. It doesn't really matter what order you dot product. It's a commutative relationship, just like addition or multiplication, not subtraction. I almost said subtraction. So n dotted with QP is going to be, well, multiply the components together. 2 times x plus 9 plus -2 times y plus 3 plus 5 times z plus 5 should equal 0. And if we were going to be lazy or run out of time, we would leave it like this. But the more typical thing to do is to multiply it out, get 2x plus 18 minus 2y minus 6 plus 5z plus 25 equal to 0. And then 25 minus 6 is 19 plus 18 is 37. Subtract 37. You get 2x minus 2y plus 5z equals negative 37. And it is not at all a coincidence that the coefficients of x, y, and z are the components of the normal vector. That is standard. So in the last minute, I'll mention that the faster way to do this is to say, hey, we know what the coefficients of x, y, and z are going to be. We know we're going to get 2x minus 2y plus 5c z equal to some constant, and then plug in the point that we know is in the plane, -9, -3, -5, to get 2 times -9 minus 2 times -3 plus 5 times -5 equal to d, and that's -18 plus 6 minus 25, which is again -17. -37, oh my God. So then we get the same resulting equation. 2x minus 2y plus 5z equals -37. It's kind of like the difference between finding the equation of the line using the point slope where you do y minus y1 equals m times x minus x1, or the slope intercept where you do y equals mx plus b, and then you just plug in your y and your x to find your b value. They both work just fine, but doing it this second way, I think, is a little bit faster. So I'll say it one more time. The components of the normal vector or the perpendicular vector will be your coefficients of x, y, and z in the equation of your plane. Always. No exception. It always feels like a thing like you learn it and then you kind of forget. You're like, why is that true again? And you have to go back and look like, oh yeah, it's because the dot product of these two things equals 0. So that's why the components here are getting multiplied by the x, y, and z here. All right, we're out of time. I'll see you all on Wednesday.